Hey everyone, welcome to this episode of Eyes on Earth. We're a podcast that focuses on our ever-changing planet and on the people here at EROS and across the world who use remote sensing to both monitor and to study the well-being of Earth. I'm your host, Steve Young. Today's guest is Doug Daniels. Doug has a number of official-sounding job titles. He is a principal systems engineer with the Aerospace Corporation at EROS. He also co-chairs the 2019 NASA USGS Sustainable Land Imaging Architecture Study Team for USGS. Now, there's a mouthful. That group is tasked with recommending what future Landsat missions should look like and what they should do. Mainly, Doug is just very knowledgeable about how satellites work and are operated, which is why he is with us here today. Welcome, Doug.
Yeah, thanks, Steve. Happy to be here.
Let's do a little basic Satellite 101, Doug. What makes up a satellite? What's it comprised of?
So that's a great place to start. So basically, you'll hear us talk about a satellite or potentially hear the word observatory. And really, a satellite is made up of two things. Number one, it's made up of a spacecraft bus and then also a payload. So let's first just start with what the payload is. The payload is the reason why we're there in the first place. The payload's job might be an imaging mission or a communications mission, but the payload is the mission. It's why we're there in the first place. The spacecraft bus really only has one purpose, and that's to make sure the payload is able to do its job. It keeps the payload alive. The spacecraft bus does all the kind of housekeeping stuff like generating power, thermal stability within the spacecraft. It keeps it oriented the way that it needs to be. And also it takes care of the communication back and forth with the ground.
So how big is a satellite?
You know, that's a great question because particularly if we think about the Landsat series of satellites, Landsat specifically is a larger satellite, maybe a little bit larger than you might think of. So remember earlier we talked about a satellite being comprised of two things, the payload and the spacecraft bus. In the case of Landsat, its payload is two imaging sensors, and those are each about the size of a kitchen refrigerator. And then the spacecraft bus itself is a little bit larger. In total, the satellite stands about 19 feet tall, and it's about 8 feet in diameter. It's a little bit octagonal in terms of how it's shaped. And then, of course, it has to produce power, so it has a solar array. The solar array is actually quite large. It's about 6 feet wide and about 30 feet long. So if you were to line the Landsat spacecraft up next to a yellow school bus, it would be about the same size.
How much would something like that weigh?
Landsat weighed roughly 6,100 pounds when we launched it. So that was the full satellite. It included the bus and the payload, and it also included the fuel on board.
I know that Landsat has been around for almost 50 years. What's happened to the size of satellites, not just Landsat, but all satellites in the last 50 years?
In short, satellites are getting smaller. Really, within the last 10 to 15 years is where the more of the substantial evolution has taken place in terms of material and sensor technologies getting smaller. And what we've seen is very small platforms. You have probably heard of the term cube satellite or CubeSat. A CubeSat is 10 centimeters by 10 centimeters by 10 centimeters. So things are definitely getting smaller. However, smaller doesn't mean more capable. Certainly in the kind of business that we're in with respect to Earth imaging, you know, we all have a cell phone, right? And a lot of cell phones have some pretty nice cameras on them. And there's nothing that says you can't put a camera like that on a very small satellite and take pictures of the Earth from space. That doesn't mean that you're producing a science quality measurement. I typically would say that smaller is better because it's less expensive. But the thing that you have to trade is the type of measurement and the quality of measurement that you're after. Sometimes physics just drives the size. For example, if you're interested in looking at shortwave infrared or thermal areas of the spectrum, then you need bigger apertures. And so those are typically outside of what would be considered really small.
You talked about launch. How do we get these satellites up in space?
Launch vehicles are really comprised of, a couple of different components. So there's obviously the engine and the structure at the bottom, which is responsible for generating the velocity. There's the common core booster, which holds the bulk of the fuel for the mission. Then there's, in a lot of cases, an upper stage engine. And then finally, there's the payload housing and the fairing, which is where the launch vehicle payload, in other words, the satellite, is housed for launch. For Landsat 8 specifically, we launched on an Atlas V. And an Atlas V is about 19 stories tall. It's one of the larger launch vehicles in the U.S. inventory. However, in the past probably 5 to 8 years, there's really been kind of a substantial evolution in launch vehicles. You've heard of SpaceX and the Falcon 9 and the Falcon Heavy. You may have also heard of the Blue Origin's New Shepard. And the really neat thing about these is they're working to push the edge of technology, particularly when it comes to reuse. So if you've never seen SpaceX take one of its Falcon 9 boosters from launch to orbit, bring it back down through the Earth's atmosphere and stick a landing on the sea or on a ground-based platform, then you're really missing something.
Can you send up more than one satellite on one of these launch vehicles?
Yeah, absolutely. Matter of fact, that's kind of the name of the game. The days of really launching a single payload on a launch vehicle, those days are disappearing rapidly. The lingo today is really primary payload and secondary payload when it comes to launch vehicles. So there'll be a primary payload that's associated with, the driving schedule for the mission and activities associated with where it needs to go on orbit, and then somebody's along for the ride. There's a lot of advantages to that because you can split costs. Launches, although the costs have come down, are still expensive. And there's lots of ways that we can share rides. The most common term used is ESPA. It's essentially a payload adapter. So a ring sits underneath, an ESPA ring sits underneath the primary payload, and then I can attach maybe as many as 6 additional satellites underneath my primary payload. You may have also heard, I brought up SpaceX earlier. They recently launched 60 Starlink satellites in a single Falcon 9.
Wow.
The key for that was the specific payload fairing and adapters, and the satellites themselves were designed to pack into a single launch vehicle, but still very impressive.
Once the satellite is in space, how fast does it travel? And give us an example of what that means here on Earth if it's going a certain speed in space.
Yeah, that's a really good way to think about it, is because in order to measure speed, you really need a reference point. And so let's use the surface of the Earth as a reference point. So if I'm standing on the Earth and I'm looking up and I'm trying to judge the speed of a satellite, it's probably counterintuitive, but the lower it's flying, the faster it's going with respect to the ground.
Why is that?
If you can imagine, the Earth is rotating. The higher that I go up with respect to the ground, the more the satellite tends to track closer to the speed of the Earth's rotation. So there's a special orbit called geosynchronous orbit, and that's the point at which the spacecraft or the satellite falls towards the Earth at the same rate the Earth rotates. So from the ground, it appears like the satellite is not moving. Its velocity is 0. It's a great platform, great orbit for communications. For orbits like where Landsat is, low Earth flying orbit, with respect to the ground, the satellite's really moving. It's in the neighborhood of 17,500 miles per hour. Now, that's a big number, and it probably doesn't mean a whole lot. But if I was going that fast, I could go from Sioux Falls, South Dakota to Minneapolis, Minnesota in less than 60 seconds. So it is moving right along.
Does Landsat have a gas tank? And if so, what's in that gas tank?
Most satellites will have gas tanks. They have fuel, and they need fuel for a number of reasons, primarily for station keeping within an orbit, particularly for low-flying satellites where there is a large degree of atmospheric drag. The atmosphere, even though we're in space, there is a little bit of atmosphere and it does drag. There's obviously gravitational effects. So a fuel tank and fuel is needed to keep us where we want to be in order to continue to do our mission. So yeah, satellites have gas tanks. Most of them have gas tanks. Landsat uses hydrazine and it has a 100 kilogram gas tank. Those small satellites that I talked about earlier, those CubeSats, they typically don't have a propulsion system, so they have no fuel.
When you say that it's traveling at 17,500 miles per hour, the hydrazine is propelling it at that speed or something else?
The fuel on board the satellite does not drive its inherent velocity. The orbital dynamics is what determine the rate in which a satellite falls towards the Earth and the speed in which it travels. Now, we can use the fuel in a satellite to change the velocity through a delta velocity maneuver, which is the typical way to do it. What that will do is it will push me a little higher So it'll raise my altitude just a little bit. And when we talk about using fuel, we're talking about burning in literally tenths of a second at a time, and maybe adding, a fraction of a meter per second to our delta velocity.
So Landsat flies at a certain altitude. How do we decide what that altitude is?
So that's a really good question. Altitudes are really determined based on the type of mission your payload needs to do. So, for example, the kind of things that Landsat does, we're interested in the Earth's land surfaces. And one of the best ways to image the Earth land surface is to fly where we are. The orbit was very specifically selected. So we fly low, basically 705 kilometers off the surface of the Earth. And if you're flying low, the Earth is big. Okay. So everybody has this picture in their mind that, hey, if I'm in space, I'm just going to look at this blue marble. That's actually not true unless you're quite a ways away. So if you're where the International Space Station is, or if you're where Landsat is, it would be akin to taking a really big beach ball, something that you could barely get your arms across, and then sticking it on the front of your nose. All you would see was this big Earth in your face. We also fly in sun synchronous orbit, which just means that as we traverse across the surface of the Earth, the sun incident angle on the ground is the same. So shadowing effects and things like that are similar from one imaging sequence to the next.
We've been talking to Doug Daniels, a principal systems engineer with the Aerospace Corporation at EROS. Doug, we didn't even get into conversations about space junk and staying out of harm's way. Will you come back and visit with us about that?
Yeah, absolutely. Looking forward to it. That's one of my favorite topics, actually.
Great. Well, until then, thanks for joining us, Doug.
Thank you.
We hope you come back for the next episode of Eyes on Earth. This podcast is a product of the U.S. Geological Survey, Department of the Interior. Thanks for joining us.